The final atomization source we're going to look at is the inductively coupled plasma, or ICP, as it's most commonly known. And this is kind of like a flame in that you are inserting your sample into a really hot thing, but it's a plasma instead of a flame. So much hotter than a flame, and made from an argon plasma. So that is the main advantage that ICP has over either furnaces or just a direct flame, is that it is significantly hotter. So this is a picture of what an inductively coupled plasma looks like inside of an ICP experiment. So it's this bright white flame here. And down here, this is a figure from your textbook with some data from a paper estimating what the temperatures are in the flame. And so you can see, we see a maximum temperature of something like 10,000 Kelvin. Usually things are measured sort of in this region of the flame where things are about 8,000 Kelvin. And as we go up the flame, the temperatures decrease, but they're still really hot, things like 6,000 Kelvin. And so a typical ICP, you can estimate it as being about 8,000 Kelvin for the sample that you're measuring. Now that's going to make it much easier to atomize things that maybe aren't as easily atomized in a flame, and it has other advantages when we talk about emission spectroscopy, which we'll get to in just a little bit. Now, how do we actually make this plasma? Well, the idea is that we make this from argon. So we usually have argon and we start this with a spark. Similar to a flame, you need some way to start all of this. And so some of the argon in that spark will lose an electron and form argon ions plus electrons. And what the inductively coupled plasma does, the inductively coupled part of it, is that these coils that you see here, that are shown here as well, these generate a radio frequency field, an electric field, that controls the electrons. And so it sort of swirls the electrons around in a circle in this area here. Oh, let me switch to a different color. The electrons get swirled around in a loop here through induction. That's the inductively coupled part. And so as the electrons get moved around, they hit more argon atoms. The electrons hit the argon atoms, leads to more argon ions forming, and then you have more electrons forming, and that sort of keeps the flame going in this process. And so that maintains the plasma. And so we're inserting energy through this electric field, this electric coil that is around the plasma, and that's what keeps it hot. So we can also come down here, and this sort of shows what this looks like from the bottom. Similar to a flame atomization scheme, we need to nebulize our sample. We need to make it into droplets. So we have, our droplets are coming up through here. We have our plasma gas, so this is our argon coming in here. And then we need something to keep everything from overheating. So you have some sort of coolant gas as well that's coming in on the outside to keep everything from overheating. And so then our radio frequency coil is here, and we have, all the tubes sort of coming together. If we come back to this picture up here, you can sort of see all these things. Oops. All these things down here at the bottom, right? This is all these things down here. Now we can do atomic absorption or atomic emission with this inductively coupled plasma, and we can put our detector either on the side for lateral viewing or on the top to view down the length of the flame. There are advantages and disadvantages to either way of doing it. The main disadvantage compared to flame or furnaces is that ICPs are more expensive, as you might expect. With all these this radio frequency coil and everything, it's not as simple as just burning some acetylene. More expensive, both to purchase and to operate. So that's their main disadvantage, and the trade-off is you can get much higher if you want to pay more. You can get much higher temperatures, which can be really important in certain applications. Okay, and so that is our final atomization source that we'll look at. And in the next video, we'll look at why the different temperature can matter, particularly for emission spectroscopy.